Here is part 2 of my interview with Martin van der Merwe. Well, that's a great overview of the challenges. So in what areas does Emerson help the industry overcome these challenges, and how does our technologies and solutions fit into the hydrogen value chain?
Well, Jim, I think it's worth mentioning first off that hydrogen production and storage is not necessarily new to us. As mentioned before, hydrogen is currently primarily consumed in refining and chemical processes. But of these industries, both of these industries actually are significant users of Emerson's technology. Our solutions and our expertise are used by these industries every day. In fact, we support hydrogen production through electrolysis at over 100 sites today with more than 180,000 measurement data points. And yes, the volume of hydrogen generated in the market by electrolysis is insignificant today, but it's just a matter of scale. And with scale, of course, there's cost reduction benefits, but there are some challenges when you scale up. On top of that, we help to address challenges in hydrogen with our Emerson greening by and greening with philosophy. With greening by Emerson, we look to support and enable our customers' hydrogen ambitions with Emerson solutions, technologies, and expertise. But we also have been involved in many of the early low carbon hydrogen pilot projects across Asia, as mentioned before, like ATCO, and other recent projects. For example, the one here in Melbourne, we partnered with Toyota on their hydrogen demonstration plant, which was a project that demonstrates the entire green hydrogen value chain from renewable solar power, battery energy storage, water treatment, production, of course, hydrogen storage, and the hydrogen refueling station. And these pilots are critical to support the tremendous amount of research and development being done to improve the efficiency and cost across the hydrogen value chain. This is where we focus on with the greening with Emerson part. This greening with is where we engage with external stakeholders to provide industry leadership, develop innovative solutions, and work with universities and research centers, as well as supporting future work in policies and regulations and safety requirements. In particular for Asia, we have partnered with bodies such as the Australian Hydrogen Council, Korea's Hydrogen Industry Association, the Clean Fuels and Ammonia Association in Japan, and several others in the region. We currently support research in these fields, including analytics, process modeling, digital twins across the value chain, solutions for hydrogen safety in transportation and storage, and also supporting that transportation and storage, whether it's compressed or liquid hydrogen, and improvements in electrolyzer efficiency and technologies associated with that. And then supporting the end users in developing their applications and use of hydrogen, especially where they have energy intensive and hard to abate processes.
Well, Martin, I love that example of the Toyota pilot because it sounds like a great pilot that showcases a large part of the value chain. Can you elaborate on what Emerson technologies were specifically used?
Sure, yeah, it's a very good example, Jim. And actually, it was great to have them participate in our Asian Emerson exchange late last year as well. As mentioned, the project covered the entire value chain from renewable solar, battery power system, fuel cell power generation, hydrogen production from an electrolyzer, hydrogen storage and distribution, and the hydrogen refueling station. As with many hydrogen projects, it consisted of several packages And Toyota's objective was to easily integrate all these packages with a balance of plant instrumentation and control and safety system that was fit for purpose. In other words, not having to overinvest, but also having the flexibility to expand and adapt as needed. Because these projects tend to, as being a pilot, tends to add some unknowns in the mix when you start to roll it out. So Emerson was selected as the automation partner on the project, since we could achieve these objectives using our Delta V integrated control and safety system, which allowed for easy integration of these packages across multiple communication protocols, including Profinet, Modbus, Ethernet IP, and all of this on a single package controller, PK controller. The solar array and battery energy storage system was one of those, what we call it a surprise, but it required a web-hosted API to interface to the control system. And to enable this, we were able to use our secure state-of-the-art edge device, and that proved to be quite successful. We also consulted on and delivered a suite of hydrogen-specific instrumentation, including pressure, temperature metering, and flame and gas detection. The flame and gas detectors were particularly important. Hydrogen flames are nearly invisible in daylight and has a low heat radiation. So it's critical to have that instrumentation there and have them accurate. So I would encourage your listeners to go to the on-demand webinar of the exchange discussion that Toyota did. I'm sure you'll share that link on your blog later. While Toyota covers most of the value chain, there are also several other projects in the region that covers other elements like hydrogen blending in India and Australia. I mentioned ATCO as that example before, and also large-scale fuel cell power generation and hydrogen refueling stations in Korea, Japan, and China. So, we certainly are kept very busy, Jim, with all the projects that's on the horizon, and because we interact across the whole value chain.
And you're definitely right. I'm going to be putting links throughout our transcript to some of these different ones you mentioned for our listeners that want to go in and learn more. So those are all great examples of Emerson's breadth in its portfolio of hydrogen applications. But Martin, were there any lessons or differences that would be applicable to larger scale projects?
That's a great question, Jim. And yes, it's one thing building a pilot or demonstration plant, but scaling it up to a larger deployment presents both opportunities and challenges. We are actually currently supporting feasibility and front-end engineering design activities for several large-scale projects in the Asia-Pacific region. So, we've seen a few things and brought a few learnings to those projects. In terms of opportunities, the obvious one is cost saving through the duplication of process units, like the electrolyzer stack design, and so on, as well as engineering and maintenance efficiencies. Some of the lessons from the gas industry that we've sort of brought over that are particularly well suited to hydrogen would be to implement a remote or integrated operations center. Having the operations centralized allows not only for cost savings, but it enables the effective use of data-driven decision making using your cross-functional teams or vendors, partners, and if they're all aided with advanced analytics and modeling, that's of course so much more efficient and a trend that we see continuing to grow. For example, identifying the optimal economic dispatch of your distributed energy resources in wind farms and solar arrays. Or you might want to optimize your electrolyzer loads to minimize membrane or diaphragm replacements. In the case of large-scale hydrogen refueler networks, you, again, may want to optimize your hydrogen distribution across the network based on demand forecast and planned maintenance routes based on predictive analytics. And Emerson has these technologies today that support the building of these operational centers through the digital twins and process and economic optimizers that can support that design and implementation of the project early, actually before the project is actually being built. And that same model and tools and optimizers can then be used on an ongoing basis once the facility is in operation to support that decision making. Many large-scale projects are phased, is the other trend we see. So their rollout is phased, again, to align with demand. We know that the hydrogen demand will increase and ratchet up over time. So there's no point in building a gigawatt straight up because you'd be supplying too much hydrogen into the market today. So again, with this phased approach, there's opportunity to optimize the design scope that provides flexibility to integrate and install new units over time while minimizing the impact and process balance of the existing running equipment. We see many hydrogen projects typically starting with just large-scale renewables that they would initially just dispatch into the grid, while the hydrogen production plant is then being built and scaled up later as offtake and supply contracts are agreed. This phased approach can present some challenges as technology is progressing and development continues. For example, right now, alkaline electrolyzers is cheaper than proton exchange membrane or PEM electrolyzers. But in the next decade, it's expected to reach cost parity, at which point you might want to switch to a more efficient PEM electrolyzer. But this would happen now after you've built your balance of plant on alkaline electrolyzer technology. So, in your design, you should consider how you can manage these different operating parameters of the two electrolyzers. And that's just a small example. Of course, there's water treatment, there's many other elements that provides variability in that design. So a phased large-scale project may also need to consider changes in the market requirements. You may initially only produce hydrogen to supply a local hub, for example, or a pipeline network. But in later phases, as you develop capacity, you might want to move to an export model. In that case, how do you plan to export that? Do you export that as ammonia or compressed hydrogen or liquid hydrogen or all of the above? So ultimately, many of these feasibility studies for large-scale projects now are looking to evaluate or simulate many of these scenarios, both economically and process-wise. So, the aim is to keep the design as flexible as possible without adding excessive cost. In my mind, having a digital twin of the assets to support the evaluation and optimize the different designs and scenarios would be a great way to build confidence in feasibility and flexibility of a project today. So I would say that's some of the solutions that we provide today, and to overcome those challenges when we scale up into larger projects.
Yeah, that is interesting, that challenge of trying to figure out that growth and demand and being flexible enough and having a mindset for a phased approach to be able to meet that. And yeah, it sounds like the simulations and the digital twin technology can really go a long way in helping some of that. So you mentioned the challenges of evolving technologies. How do you see Emerson adapting and innovating to address some of these challenges?
Luckily, Jim, innovation is at the heart of Emerson's purpose, and we continue to invest in R&D and partner with research bodies to ensure we can support our customers as the processes and operations technology advance in hydrogen. We have a strong track record with our investment to support the development of severe service valves for cryogenic liquid hydrogen applications, as well as our micromotion Coriolis flow meters designed for high pressure, high flow hydrogen dispensing that improves refueling times for heavy duty freight applications. So we have many of these examples. I believe not only will it be important for customers in the hydrogen industry to leverage any new technology and solution, but also to ensure that the equipment and the technology that they select are robust, reliable, and fit for purpose. The industry will be very competitive very quickly, and reputation will play a key role for the future of the success of any business in the hydrogen industry, I believe. So, while talking about innovation and evolution of the technology, I think it's also important to consider the impact that regulations and standards will have in this regard. This is also why Emerson have representatives that participate in standards developments and to ensure that we're aware and prepared for regulation changes as they progress, particularly across the Asia-Pacific region.
Well, Martin, it's been a great discussion, and I hope our listeners enjoyed it as well. Before we wrap things up, where can our listeners go to learn more, and how can they connect with us on any specific questions that they might have?
Well, Jim, I would say, a great place to start is our sustainability and decarbonization webpage. Through that, your listeners can find out more about our sustainability initiatives, our solutions, keep up to date with the new technology that we roll out and new solutions in the space. So that would be a great start. They can also reach out to us through the podcast series. Jim, I believe you're sharing the contact details of our Emerson Sustainability Decarbonization representatives for each of the countries here in Asia Pacific. So feel free to connect with them if you have any queries or need assistance.
Yep, that page is fresh off the press, so that's perfect. I'll add links in the transcript that we have to these sites, as well as other things throughout the course of our discussion. So Martin, I want to thank you so much for joining us today and sharing some of your insights on the future of hydrogen across the Asia-Pacific region.
It's been a pleasure. Thanks a lot, Jim, for having me on. It's been great.
Well, thank you. For our listeners, this was the second in a series of our Asia-Pacific Sustainability and Decarbonization podcast. Do follow our page for details for the next podcast, where we will cover specific segments such as renewable energy, carbon capture, and more in greater detail with our subject matter experts from Asia Pacific.